Ever wonder how AI models like GPT or BERT solve new problems on the fly, without retraining? It's like magic, but there's a mathematical foundation beneath the surface. Today, we're diving into how transformers, the engines behind these models, use geometry to learn from just a few examples. Let's unravel the hidden math that makes this possible. Imagine data as a hidden treasure map. Instead of a flat grid, it's folded into a complex shape, like a crumpled piece of paper in 3D space. This shape is called a manifold, a mathematical concept where data lives on a lower dimensional surface, even if it's embedded in a higher dimensional world. For example, a dataset of human faces might look 2D because faces are flat, but in reality, it's part of a 3D world. The true structure, its intrinsic dimension, holds the key to understanding it. Now here's the twist. Transformers don't just memorize examples. They see this hidden geometry. A groundbreaking study shows these models naturally exploit the manifold structure of data. Picture a spotlight shining on the most relevant clues in a prompt, not randomly picking pieces of information. This is where attention mechanisms come in. Like a super-focused detective, they highlight the parts of the data that matter most. But how do they do this? The researchers linked transformers to kernel methods, a classic tool in statistics. Think of kernel methods as a way to weigh how similar examples are to each other. Transformers, with their attention, do something similar. They dynamically assign importance to different parts of the prompt. This connection lets them mathematically prove how they can adapt to new tasks using just a few examples, like learning to solve a math problem after seeing one worked example. The study's biggest revelation. When dealing with smooth, structured data, like a spiral or a sphere, transformers achieve near-perfect performance. Their error rate depends on the data's intrinsic dimension, the true complexity, rather than its ambient dimension, the space it's embedded in. This means they're way more efficient than traditional models, which get bogged down by irrelevant details. It's like navigating a maze by focusing on its skeleton, not every wall. Why does this matter? It explains why transformers excel at tasks like language modeling or image recognition, where data hides in complex, low-dimensional patterns. It also opens doors for smarter AI. Think robots that learn faster or scientific models that handle messy real-world data. The future isn't just about bigger models. It's about models that understand the shape of the world they're trying to learn. But here's another layer of the puzzle. How do these models stay stable? Let's talk about neural network weights. Think of these as the strength of connections between layers, like the pressure in a water pipe. Too much pressure and the pipe bursts, overfitting. Too little and the water barely flows. A study on the B4 model shows there's a mathematical ceiling on these weights, something like O, D4 letter 21132 M4. Here DL and M represent the model's size, complexity, and depth. This ceiling acts like a safety valve, preventing the model from becoming too powerful and memorizing noise instead of learning real patterns. Now let's connect this to kernel methods, specifically Gaussian kernels. Imagine predicting the weather based on temperature data. A Gaussian kernel is like a spotlight. It shines brightest on the data points closest to your prediction, fading out as you move away. This helps the model focus on relevant information, smoothing out noise. The math here ensures distant points have less influence, keeping predictions stable. It's like using a magnifying glass to zoom in on the most important details, without getting distracted by the background. But here's the kicker, these two ideas work together. The weight bounds keep the model from getting too wild, while kernel methods ensure it pays attention to the right data. Together, they create a system that's both powerful and reliable, like a chef who knows exactly when to add salt and when to let the ingredients shine on their own. Understanding these concepts isn't just academic. They're the backbone of models that power everything from language translation to medical diagnostics. Next time you interact with AI, remember, it's not just magic. It's math, carefully tuned to balance creativity and control. Thanks for watching. If you want to see how these ideas apply to real-world AI, hit subscribe and stay tuned. Until next time, keep exploring the science behind the tech.